Okay. Learning outcome 2 then is the rates bit will take up most of what we're doing. The equilibrium is mostly sort of about a session and a half perhaps, and a lot of it is doing practice questions and then giving you the assessment ones to do. So, you know, it's not a very, well, not a large part of it. But the rates bit does take a while. Okay, rate of reaction then. So, you know, just as a starting point then, what is a reaction? Well, we start with our reactant or reactants, and we end up with our product or products. Now, what we will eventually get to is, with equilibrium, we'll be looking at the idea of a reaction being reversible. But you would still have, from left to right, you'd have reactants to products, but also from right to left, you'd have reactants to products. And it's a matter of, with the equilibrium section, finding out which of the, well, what point you reach in terms of concentrations when the rates of the reactions are equal in both directions and there doesn't appear to be any more change. So that's something to return to. But this idea of a reaction then, we talk about reactants, we talk about products, and then the idea of rates. Well, what is a rate? A rate is something which involves a period of time. That's really important. It's usually something about a change over a period of time, isn't it? A rate. So, you know, the rate of a chemical reaction, we're going to need, obviously, you know, tighter definitions for that. But it's change over a period of time, and it could, for example, be something like speed. Would be a change in distance over time, and it's your rate of movement, isn't it? Speed. You could have acceleration, which is the change in speed over time, and various other rates as well. I'm trying to think whether we've met any other rates. We've had I can't think of any that we have met, actually. I don't think we've really considered rate yet in a general sense. But what you're going to do over today and tomorrow, you're going to try out a couple of little investigations to look at methods of measuring. Next week, I think you've got a couple more. So you're actually going to get quite a lot of practical experience for different ways of measuring rates of chemical reaction. So you're going to have, because of the period of time involved, you're going to have something, and then you're going to have a time unit, which, because it's per minute or second or year or week or whatever you like, is going to be to the power minus 1. All right, so it would be something like, oh, I need something to put as change. I don't want to put for the rates, I don't want to actually use that one, but it could be something like meters per second. All right, or you could have, trying to think of one that would fit into the environment unit, kilojoules per square meter per year for energy changes. So it would be the rate of energy transfer in an ecosystem. Overlapping everywhere here. But yeah, you could have kilojoules per square meter per year, I think is just Y. Right, but because it's got a time unit in there, so per unit of time, it's a rate. Okay, so a rate is something that changes over time. Now, if we think about chemical reactions, then different sort of units, aren't they? And we might have moles per second, or if we're looking at changes in concentrations, of course, moles per decimeter cubed per second. We're going to have some, you know, interesting units to consider. But different reactions happen at different rates, don't they? You know, I mean, slow reactions might include things like things that you see happening in the environment, like, say, rust formation. Doesn't happen rapidly, does it? It's a gradual process. That sort of rust or copper, oxidation of copper, that sort of thing that forms over, I don't know, weeks, months, perhaps. Whereas we also have some reactions that go really rapidly. I mean, we had one in the fume cupboard that went extremely rapidly, and we had one in the water bottles, the whoosh bottle, a very rapid reaction. So you've got the extremes, really, of extremely slow or explosive being extremely quick. And so there's no there's no rule. There's nothing that tells us how fast they'll be. Oh, the metals in water, they were fast ones as well, weren't they? So what we've got to consider is how are we actually going to measure rate of reaction? And you're going to look at factors that have an impact on rate, but you've got to have a way of looking at rate first, haven't you? You've got to be able to measure rate. So well, you've got two options. All right, so two options for measuring the rate, and the reason I started with that overview of a reaction you can look at the speed with which your reactant disappears, or you can look at the speed at which your product appears. So you've got those two possible angles, and it will depend what your reactants and products are, won't it, as to how easy that is. And you can use either, and it depends. Can you measure something disappearing very easily? Not necessarily. Let's use an example that works for today: photosynthesis. I've got to throw it in everywhere, haven't I? One of the practicals that we're supposed to be able to do with photosynthesis is to look at the effect of light intensity, for example, on the rate of photosynthesis. And if you've done a bit into that this morning, you'll know, obviously, as light intensity increases, the rate will increase, and then as light intensity decreases, it'll go down again. And there's a practical that you can do theoretically, but I've never got it to work yet. I'm going to have to next year because it's a required practical on the GCSE. I'll have to find a demo of it. Where you put a piece of pondweed in a funnel with a tube of water on the top, and you can move a light closer or further away, and that changes the rate of reaction. Now, the reaction in photosynthesis, as you'll know now, is your reactants are what's going in? Carbon dioxide and water. Oh, you worked hard at that this morning. And what's coming out the other side is oxygen and, well, it's glucose to start with, yeah? All right, the sugar. Now, out of those things, is it possible to measure the uptake of carbon dioxide? Not really, is it? The uptake of water with a pondweed? Not really. The production of glucose? Not really. Oh, production of oxygen from a water plant. Does it produce bubbles? It does. So yeah, so you use the reaction, you look at the aspect of the reaction that's most measurable, and you use that. And you're going to look at several options, really just for the sake of different practical techniques. Particularly tomorrow, where you're not all going to do the same thing. You're going to try out different ways of measuring the same reaction. So our two options are, first of all, the disappearance of reactant, and then our alternative is the appearance of product. So, what sort of things, what sort of measures could you make? Well, you can look at, there'll be all sorts of things that we can't do because we haven't actually got the equipment, but for the bubbles of oxygen gas, for example, what would you actually be measuring? You could just count the number of bubbles, but probably better to measure the volume. Yeah, so you could have volume of a gas. Other obvious things that you might measure. You could, yeah, that's a little bit harder, but you could, yeah, change in temperature perhaps. So a little bit harder to actually get the rate from that, but it's because heat is sometimes a product. Theoretically, you can. I mean, that's what you were doing, wasn't it, in the enthalpy one? Hard to get it with the rate, though, I think. You can have, yeah, change in colour. And you can do that by eye, and in fact, you are going to do change in colour for the assignment, sort of. It's not so much colour, but it's whether you can see through a solution or not. And you put a piece of paper with a black spot on the other side of the solution, and when it disappears, that's your end point. And you might think, well, that's a bit sloppy. It's incredibly accurate. It's amazing how accurate that is. But you're going to do a colour one this afternoon, sort of. But there are also pieces of equipment that will measure colour. We have a thing called a colorimeter that actually measures colour against standard values. But I haven't used it in all the time I've been here. There are much more elaborate versions of that called spectrophotometers that measure the amount of light that can be transmitted through a solution. And you can actually put a reaction into one, and it will plot a curve of the change. So, you know, we don't have one of those. But my other half at Yarmouth was saying that she discovered somewhere online, and I can't find it, so I'll have to ask her again. And it's actually based at UEA, where they do spectrophotometer in a case, or a suitcase, or something like that. And there's a tutor at UEA who goes around places bringing this thing in a bag and demonstrates it. If I can track that down, we might consider that. Get him in. So changing colour, or similarly sort of absorbance of light. So that's a sort of another aspect of it, really. We've missed one of the most obvious things, and that would be change in mass. All right, the increase or decrease in mass. I've not written these consistently, but this could be increase or decrease. What else have I got on my list? You could, yeah. Where are you getting them from? Change in viscosity. How would you measure that?
You didn't really go from liquid to solid.
Well, yes. Now that's the cement thing is actually, that's quite interesting. And yeah, Jill's not here at the moment, but she worked for a while associated with a project where they were looking at cement in the mixer lorries that was setting too quickly. So they were, just driving a big brick around, I think, I seem to, I'm not sure what she had to do with it, but, and I'm not sure that was exactly what it was, but yeah, they obviously, there's additives they put in, aren't there, to slow down the rate of setting. And yeah, that's a possible one, isn't it? Also, how about, electrical conductance or something like that? Because if you've got ions in a solution, then it'll be very conductive. But if those ions then form another compound, then, it may not be so. So electrical change, change in conductance. Oh, we're getting all sorts of curious stuff here. We've actually sort of gone beyond, conductance. Beyond, the realms of things that we can measure. We can measure things like changes in mass. We can measure volumes of gas quite easily. With changes in mass, you've only got to use a balance, haven't you? Electronic balance. Changes in gas volume, we've actually got several options for that. You could quite simply, well, for gas volumes, you can almost invent your own little setup, but there are standard ways of measuring gas volumes that you can have. If you've got your reaction going on in, usually it'll be a conical flask. So here's our reaction in here. We would need to put a stopper or bung in it. Always a bit of a test of your drawing skills. And if we're getting bubbles coming out of here, then we've got two ways of measuring them. Which one shall I go for first? Let's go for the slightly more complicated drawing. And I'm putting these in because these are what you're going to use tomorrow. Well, you're going to use one of them. I think you'll use this one. You can have tubes connected up like that. And then if you have a tank of water or a big dish, I forgot what we call them. It's all right, it'll come back to me. And you have a special piece of equipment in here with some holes in it. It's called the beehive shelf, that thing. And then you just put, you could have an upside down measuring cylinder on here. Something like that. Oh, that's quite artistic, but now the water's overflowing. All right, your bubbles come up here. And you can measure, you can time it, can't you? So, you can say after 30 seconds, a minute, minute and a half, 2 minutes, how far's it gone? And you'll get your rate of reaction. Yeah? Another option for doing gas volume, which I don't think you're going to use tomorrow because we've got it lined up for one of next week's, is a thing called a gas syringe. And it is what it says it is. And if we have our flask again, I'm not sure I've left myself enough space. Oh, I'll work it out somehow. Again, right, same sort of setup with the reaction. It's going in here producing bubbles. But we then connect this up to literally a gas syringe. It is a piece of equipment which looks like this. And again, it's got a scale on it. And the connection, we have great fun setting these up. Obviously, that would be held in a horizontal position using a clamp stand. All right, but you can read off as the plunger bit is pushed out there. You can read what the volume of the gas is. So very straightforward. The one you're going to do tomorrow, you're going to use the this one, that sort of technique, and compare that against. Well, you're going to look at a reaction between marble chips, which is calcium carbonate, and hydrochloric acid that produces carbon dioxide gas. And you're going to try this one, which is measuring the amount of gas that's produced. And you're also going to try putting the reaction flask on a balance, an electronic balance, and measure the loss in mass. Because obviously as the carbon dioxide is given off, the mass will fall. See if we get similar sort of graphs. There's going to be a lot more graph drawing. There's one thing you will be expert at by the time I've finished with you. It'll be drawing graphs. You'll be doing it in your sleep. You'll be finding any excuse to draw a graph. But, to be honest, the further you go, the more you'll have bits of equipment that will do it for you. You'll put a reaction into a machine. You won't have to do anything. It'll just give you a printout. You don't have to draw the graph. You don't have to take readings. And I think that's a bit of a pity. Yes, it makes life quicker, but This part, of course, is about understanding what that machine is doing, really, because you have to do it yourself. So you've got a couple of options there for measuring gases. If you wanted to measure a loss in mass, then very simply, you put your flask onto a electronic balancer, you set the reaction going, and there you go. After you take a reading every 30 seconds, and the mass should change. Now, the general sort of equation that we're going to need, it's going to need to make some sort of comparison of our quantity over time. So it might be the volume, it might be a mass, it might be some of those other things if we have ways of measuring them. It might be likely to be a change in absorbance if you're using a spectrophotometer, which you would then relate to a calibration curve to give you concentrations. Well, like I say, it's not what we do. If we're looking for just our basic rate of reaction, we need some sort of difference over a period of time. So it's going to be the amount of a reactant that's used or the amount of a product that's formed over the time that it takes. All right, so this is, like I say, starting at the very simplest level, so amount of reactant used, I'm not sure I can fit it all in, or product formed. Oh, just about. There we go. And divide that by the time taken. So, you might have, let's say, 500 centimetre cubed of gas produced in 10 seconds. And then you can work that out as a rate, a volume per second. Now, the next thing to start looking at then is the factors that affect the rate of reaction. And this is then what will lead us on to a bit of practical work for this afternoon. And we're going to start just with an overview of factors that affect the rate. We can look at it sort of from either point of view. Will the rate increase? Will the rate decrease? This section actually will fit very nicely alongside the bit we do on enzymes, because when we get on to enzymes, we are looking there at factors that affect the rate of reaction, and that is part of the exam for that. So yeah, I seem to have it all nicely lined up for you. I think the other lot are really struggling. Some of the biochemistry is not lined up properly at all with the chemistry they're doing. However, this means I have to sort of sidetrack to talk about bonds in organic compounds and things like that. Okay, so let's consider what sort of factors might increase the rate of reaction. So rate increases if, all right, okay. What about temperature? What change in temperature will increase the rate? Increase, yeah. Hopefully you're thinking kinetic theory and movement of particles and all that, yeah. So temperature increases. I could have just put an up arrow and temp, couldn't I? Sorry? Both ways. If temperature decreases, the rate will decrease. It's not a reaction as such, no. The rate, it's, yeah. Oh, yeah. Yeah. Oh, for an endothermic reaction, yeah, where you're putting heat into it, I don't think that, it won't make any difference. If you raise the temperature of the particles, they will move faster. For an endothermic reaction, it's going to use that heat. For an exothermic reaction, it generates its own heat. But what that endothermic reaction was doing was cooling the environment. So you sort of have to be careful with that. We get a bit tangled up with that as well when we get onto equilibrium, because you have to think sometimes of heat either being a reactant, because heat is a reactant in an endothermic reaction, but it's a product in an exothermic one. But yeah, I mean, it's yeah, if you move your particles around faster, they are going to collide more often. What about if we, what about concentration? How would we increase the rate of a reaction? What would we do to concentration? Increase it, yeah. Now, these are, you've got to remember, we're working at sort of GCSE level at the moment. These will get more complex. Concentration, well, concentration works if you're looking at a solution. If we were looking at gases, what's the equivalent for gases rather than concentration? Pressure, yeah. If you think about it, you know, you've got, let's say, a container with so much gas in it. If you decrease the volume of that container, you've increased the pressure, haven't you? But you've increased the concentration. You've given the particles less space to move around in. So that's pressure of gases. I don't know why I'm writing all the increases out every time. If you've got, let's say, solid reactants like you're going to use marble chips tomorrow, I mean, I could give you a chunk that size, or I could give you powder. Surface area, yeah. So if you break solid reactants up, so you'll increase the rate of reaction if surface area increases, and that's, you're going to actually test that. We've got 3 different sizes of marble chips. It's very, very rough, 3 different sizes, but they usually work quite nicely so that you can actually draw 3 different graphs to show 3 different rates of reaction. You can, yeah, actually, rather than comparing the loss of mass method and the production of gas method, choose one and then, yeah, do the 3 different sizes of marble chip, and you find that you do get, even from, you know, quite a very simple sort of arrangement, you get different rates. The other thing that we haven't really come across yet is catalysts. All right, now that's what enzymes are. Enzymes are biological catalysts. But a catalyst is something that speeds up a chemical reaction without being used up itself. It provides alternative routes for the reaction to take place that require less energy to get going, really. But we're a little way off actually you know, explaining that yet. But yeah, I will demonstrate something with a catalyst tomorrow, but I will show you a much better YouTube version of it, which, yeah, we don't do because it's too messy. But yeah, if you add a catalyst, you can speed a reaction up quite significantly, and then you can extract the catalyst at the end and reuse it, and that's you know, it's a very useful thing in industry. So we will we'll need to sort of consider that. Now, if you were, for example, to raise the temperature of a reaction, would you get more product in the end? Ultimately, no. No. I think you're following my line of thought now. There was a sort of puzzled look as to what I meant. But what we're looking at is just how fast you get there, isn't it? So it would be like saying, you know, if you drive from here to Yarmouth at 40 miles an hour, compared with driving from here to Yarmouth at 100 miles an hour, you know, do you end up somewhere different? No, you don't. You still, well, you might actually end up in a police cell, perhaps, but yeah, I have been to Yarmouth at 100 miles an hour, but that was approximately 30 years ago. Yeah, it was when my second son was on the way. He nearly arrived in the car park. Uh, yeah, it wasn't until afterwards my husband said, "Do you know we hit 100 going up the dual carriageway?" It was a good job he did. But yeah, you still end up at the same place, you just get there quicker. Yeah, which was just as well, really. So you don't get any difference, you know, in your end state. You can't, can you, really? You know, you've only got a certain amount of reactant, so you can only produce so much product. And if you were to look at it graph-wise, let's say at a lower temperature or a lower concentration or a lower or larger pieces, let's say, you might expect a reaction that went off, I don't know, they all have to flatten off in the end, but it might go off like that, all right? So it, you know, it speeds up at the beginning, you know, keeps going, but then it flattens off. And then if you, all right, what would that be? Low temperature, well, that's just for example, or concentration. I'm going to use that abbreviation, CONCON, for concentration. If we were to raise the temperature or the concentration, it would just go off faster and get to the same point quicker. All right, so you know, it doesn't make any difference to that bit, but this is your higher temperature or concentration. And the important bit here is actually going to be what we call the initial rate. Now, what we have to do is to sort of define some way of identifying the initial rate. And the reaction that we use, this one where the black dot disappears in the solution, we use that disappearance point as an indicator of our initial rate of reaction. Really because there's no other way of measuring it. So if this was, yeah, this would be, you know, your vertical would just be your amount of product, and your horizontal would be the time. And if we look generally then at changing conditions, like temperature and concentration and pressure, it's really about collisions. Right? The significant thing here that changes the rate, the factor that actually changes rate, is collisions. So we will come back to collision theory, but collisions between particles, as long as they've got enough energy, and if you remember back from the organic mechanisms, as long as they're the right way round as well. Do you remember they had to be just in the right orientation with those mechanisms you drew? You know, they wouldn't react that way on, but they would react that way on. So the collisions with enough energy and in the right orientation, if we're going to be precise, to be absolutely honest there. Okay, so the collision is the key, and it's a word that needs to come into descriptions that we're using. Okay, right, we're now going to try a bit of practical work and see if we can actually get some data. It's, yeah, Jill's had to fiddle with some concentrations to actually get it to a point where it will cooperate for us.